Good morning, champs! Today, we're exploring a powerful technique, converting Cartesian coordinates, which use x and y, to polar coordinates, which use the radius and angle. In Cartesian coordinates, we identify points on a grid by the x and y positions. In polar coordinates, we use two different values to describe any point: r, the distance from the center, and phi, the angle. We'll see how this shift helps us find the area of a circle in a simpler way. Let's start by looking at an area represented by a double integral in Cartesian coordinates. Here we describe an area in terms of x and y over a certain region. Now, what if we could describe this area using polar coordinates? This is where our transformation magic begins. We'll adjust the integral, introducing something called the Jacobian determinant, which accounts for the way areas scale differently in polar coordinates. This determinant acts as a scaling factor, allowing us to accurately measure areas. Now, we're ready to switch to polar coordinates. Our new variables are r, representing the distance from the origin, and phi, representing the angle from the positive x-axis. In polar coordinates, we can describe any point using these two values. The connection between Cartesian and polar is simple. X is equal to r times the cosine of phi, and y is equal to r times the sine of phi. This allows us to move between the two coordinate systems whenever we need. Next, we calculate the partial derivatives of x and y with respect to r and phi. This helps us build the Jacobian matrix, which scales areas properly in the new coordinate system. We start with x equals r times cosine of phi. The derivative of x with respect to r is cosine of phi, and with respect to phi, it's minus r times sine of phi. For y, which is r times sine of phi, the derivative with respect to r is sine of phi, and with respect to phi, it's r times cosine of phi. Arranging these values into a matrix, we find the Jacobian matrix, which looks like this. The matrix includes cosine of phi minus r times sine of phi in the first row, and sine of phi r times cosine of phi in the second row. The determinant, which is simply r, is our scaling factor. This helps us measure areas accurately in polar coordinates. Now let's apply this transformation to the double integral we started with. In Cartesian coordinates, we integrate over x and y, but in polar coordinates, we integrate over r and phi. The scaling factor we calculated from the Jacobian determinant, which is r, is included in this integral. This factor adjusts our area measurement as we switch coordinates. Let's look at the region we're integrating over. In Cartesian coordinates, a circle is defined by the equation x squared plus y squared equals r squared, where r is the radius. This gives us a circular region centered at the origin. In Cartesian coordinates, the limits for y depend on x, making the calculation complex. In polar coordinates, the region is simply described as r going from 0 to r, and phi going from 0 to 2 pi. This avoids any complex limits and makes our integral much simpler. Now let's calculate the area of a circle using our new polar coordinates. We'll set up an integral for the area of this circular region. First, we write the area as a double integral over the region D. In Cartesian coordinates, this would be the integral of 1 with respect to x and y. This is essentially saying the area is the integral of the constant function 1, representing a flat surface over our region. In polar coordinates, we can use the transformations we derived earlier. Our function remains 1, as it's independent of r and phi. Now we set up the integral with the scaling factor from the Jacobian, which is r. So our area integral becomes the double integral of r with respect to r and phi. Finally, we can calculate the area step by step. 1. First, we integrate with respect to r from 0 to r. This gives us r squared divided by 2. Next, we integrate with respect to phi from 0 to 2 pi. This final step gives us the area as pi times r squared, the familiar area of a circle formula.